Hey, what is up, everyone? Mr. Schleicher here. In some very trying coronavirus times, this is going to be our first video notes of the week. We're moving on to this new unit, basically called gases in general. Today, we are going to talk about pressure and kinetic molecular theory, what exactly those things are, and how to answer questions with those. So our learning goals here, we want to define what pressure is. We want to describe how gases actually exert pressure. We want to perform calculations using this guy named Dalton's law of partial pressures. And then we want to describe kinetic molecular theory, which is basically what an ideal gas is. So it might all seem like gibberish right now, but hopefully it all makes sense by the end of this video. So first of all, what is pressure? Well, pressure is an amount of force exerted over a certain area. In physics, they might make you memorize this formula. Pressure is equal to force divided by area. But in general, you can think of pressure as something like, let's say, maybe a 10 kilogram box might exert less pressure than a 10 kilogram high heel because a high heel has the same amount of weight over a smaller amount of area. So how does gas relate to pressure here? You might have heard of like tire pressure before, maybe the pressure in a hot air balloon, things like that. Well, from the atmosphere, pressure is caused by gas molecules. So imagine like we talked about solid, liquid, and gas already, but gas molecules are just bouncing all around the room, and those gas molecules are physically colliding with surfaces around them. So they're hitting the walls, they're bouncing off. They're hitting other gas molecules, they're bouncing off. They're hitting our lungs, they're hitting our face. This is all happening all the time. Now, when you have more of these collisions, when these gas molecules are whamming you more often, that means there's going to be more pressure. Less pressure means that there's less collisions happening. There's less forces happening against you. So let's pause and think about these two questions here. First of all, what do you think causes pressure from a gas? And what do you think happens to the pressure of a closed container if you add more particles or moles of a gas to it? Okay, so we did say collisions cause the pressure from a gas, collisions from a gas molecule. And let's say we have this closed container and it had like 3 gas particles in it. So maybe there's like 3 collisions per second. I don't know. Well, if you add like 3 more gas particles to it, there's going to be, 3 more collisions per second in that rate, which would increase the pressure. So pressure increases if you have more gas. So for example, if you have like a balloon, how do you increase the balloon's pressure? You just blow up the balloon. You insert air into it, and that increases the pressure. How do you increase tire pressure? You insert more air into the tire. Okay, what do you think happens to the frequency of the collisions of gas to the walls of a closed container if you make the container smaller? Okay, so let's say that maybe we have this, and in chemistry they use this example a lot. I struggle to think of a real world example, but let's say you have this like closed container and then this piston here. This piston's movable, it could go up and down, but this is all airtight. So let's say that piston has a bunch of these like gas molecules in there, and then you like compress it. You shove that piston down, and these gas molecules, the same exact gas molecules, now have less space to roam around. Well, because there's less space to roam around, now those gas molecules are more likely to hit the edges of the container, hit the walls of the container. So that is going to make pressure increase. if you have less space for those same exact gas molecules. Okay, we'll talk more about those pressure relationships later, but let's talk about how did we come up with pressure in the first place. Well, there is this device called a Torricellian barometer, and it's shown right here. And basically what happened is this long glass tube, someone put a bunch of mercury in it, mercury being a liquid toxic metal at room temperature. And they put all this mercury in this tube, and then they turned it upside down and put it into this dish. And what happened is that the mercury fell down the tube and formed a vacuum. A vacuum just means that there is a space without any air. You might already know that word from like vacuum cleaner or like the vacuum of space. But anyways, there's this empty space here where the mercury left behind, and it turned out that whenever someone measured the distance of that empty space, it was always 760 millimeters that it fell down, that the mercury level fell down. So they came up with this measurement here. They said that, well, we're going to say 760 millimeters of mercury, or Hg, that's a symbol for mercury, is going to be our measurement of standard atmosphere. Basically, the air pressure of our Earth's atmosphere at a standard day. And they noticed maybe the weather would result in changes in this level of mercury. Sometimes the mercury would go up, sometimes the mercury would go down. So that would change what you would measure as the air pressure. 760 millimeters mercury is actually the standard pressure of the Earth's atmosphere at sea level. Now, you might know that if you go into the mountains, it's kind of harder to breathe. Maybe athletes go to train in the mountains a bit. So as you go up and above, farther away from sea level, your air pressure starts to decrease. Maybe instead of 760, it'll be 750. Maybe it'll be 700. Maybe it'll drop to 600. It'll be lower and lower. And there's actually all these other units that have been since used to measure air pressure that were invented. So, for example, we talked about 760 millimeters of mercury. Turns out a millimeter of mercury, someone else said, let's call it torr instead. So torr is a unit of pressure that is spelled T-O-R-R. Now, someone else thought, wouldn't it be a lot easier just to say the Earth's atmosphere, let's just call that air pressure 1 atmosphere at sea level. So 1 standard atmosphere, that was another unit that was come up with, and the abbreviation for that is 1 ATM, not automatic teller machine, but a unit of pressure, meaning atmosphere. Finally, in physics, they like to work with different units. They like to work with pascals. So another common unit of pressure is this 101.3 kilopascals, this kPa. That is equivalent to this pressure of the atmosphere at sea level. So you can actually really easily convert between all these units using dimensional analysis with all of these conversion factors right here. It's all just one big conversion factor. So we are going to try to convert here. They're all directly proportional. So all you need to do is set up a fraction, and I'll show you now. So how many millimeters of mercury would be measured if there were 2.3 atmospheres measured? Okay, so we are given a measurement. So what would we do first? We would write it down first, 2.3 ATM. And then we have to use a conversion factor and think about how do we cancel this out to get to what we want. So we know that we're trying to get from atmospheres to millimeters of mercury. So it looks like in this conversion factor, there's 1 atmosphere for every 760 millimeters of mercury. So I'm going to go back over here, and on the bottom, I know I need to write atmospheres to cancel that out. And there's 1 atmosphere for every 760 millimeters of mercury. And that's all you do to set this up. So you're going to do 2.3 times 760. And I have to do this calculation right now. 2.3 times 760. And I am getting around 1,700 millimeters of mercury as my answer here. Okay, next example. The pressure of a gas is measured to be 49 torr. What is that in atmospheres and in kilopascals? Okay, so two different problems here basically. Both of them want you to start off with 49 torr, and one of them wants you to convert it to atmospheres. The other one, let's convert it to kilopascals. So 49 torr, let's use that first. And if you look at the conversion factors from the last page, it looks like 760 torr were equal to 1 atmosphere. So torr cancel out because you put the torr in the bottom there. And then in that calculation, you have to do 49 divided by 760. So let's see, 49 divided by 760. Looks like I'm getting about 0.064 atmospheres. Okay, next part of the question, it's asking for kilopascals. So let's start with that 49 torr again. And according to the conversion factors on the last page, whenever we had 101.3 kilopascals, again, we had 760 torr. So the torr will cancel out. And then all we have to do is do 49 times 101.3 divided by 760 to get our answer. And I'm getting about 6.5 torr as our final pressure here. All right, now we want to talk about Dalton's law of partial pressures. So in 1803, John Dalton summarized some observations of gases with this quote. He said that for a mixture of gases in a container, the total pressure exerted is the sum of the pressures that each gas would exert if it were alone. Okay, so what does this mean? Basically, let's say we have a container, I don't know, maybe some airtight box, and we just have pure oxygen in there, so pure O2. And maybe pure O2, maybe there's like 1 atmosphere of pressure of that in there. Okay, and maybe we have this different container here. Maybe it has pure nitrogen gas, N2. And let's say there's only 0.5 atmospheres of pressure in that, like maybe there's less gas or something, and it exerts less pressure. Okay, so these are both pure containers of gas, but what if we put both of these gas samples together in the same exact container at the same size container as well? What would happen? Well, this mixture of O2 and N2 in this one container of the same size, now that's going to have a pressure of 1.5 atmospheres. So really, the total pressure of this mixture of gas is just all the pressures that the individual gases would just add up to. It's really quite simple. This law is known as Dalton's law of partial pressures. Mathematically, you might see this fancy equation where the total pressure, or P subtotal, is equal to P1 plus P2 plus P3. Basically just the pressures of your individual gases. So pressures of individual pure gases. And P total is just the pressure of the total mixture there. Okay, so in this following illustration, you might notice that, okay, basically the exact same thing I drew before. Maybe we have this like first gas sample, I don't know, let's call it blue gas, some random blue molecule. And we have the second gas sample, let's call it the red molecule, for instance, or orange, depending on how you see color. And it's exerting, both gases, they're exerting pressure by bouncing off the walls of the container. They are hitting that wall, hitting force over a certain area, and maybe like the blue gas has less pressure than the red gas because, you know, there's less particles bouncing around. But whatever pressure the blue gas and the red gas are at, if you put both of them in the exact same airtight container, the total pressure of that would just be the pressure of the first gas plus the second gas. That's it. So let's look at a couple of examples here. A student collects 1.4 atmospheres of gas over water. The student determines the pressure of water was 0.2 atmospheres. What is the total pressure in a container? Okay, so 1.4 atmospheres of gas over water. What does this even mean, like collecting gas over water? Well, it turns out the main method to actually collect gas in any sort of experiments back in the day is collecting it over water. The reason for this is because water, it happens to make a pretty good airtight seal. So when you're thinking about an experimental setup, what this looks like is maybe we have some sort of container that we want to capture gas in, and it's turned upside down, so the opening is facing down. And then what happens is you put that container and you submerge it in water. So maybe there's a bunch of water here. Like this is filled with water, you turn it upside down into a plate full of water. So then everything is just water right now. That's water, this is water, you get the picture. And then in this experimental setup, what happens is often maybe there'll be some reaction in some random container here. Let's use this little flask. And then maybe some tubing will be attached to the opening of the container, and any sort of gas that's released from the reaction will then be collected in this container here. So then as this container fills up over time, the water will be more and more displaced, and you will have more and more gas here. And you actually see more and more empty space here that you can see the gas in. Okay, now that we know this experimental setup, like what is going on here, how do we solve this problem? Okay, we are collecting gas over water. The thing about collecting gas over water is that in the air, there's always a little bit of water vapor. So if you're collecting gas over water with this method here, you have to account for the water vapor. The water vapor is a gas that's going to exert a little bit of its own pressure. It's going to contribute to the total pressure. And in this case, that amount of pressure that the water vapor has is 0.2 atmospheres. So they tell us that we have 1.4 atmospheres of gas from maybe the experiment or wherever, who knows. And then the water vapor pressure is 0.2 atmospheres. What is the total pressure? I know I explained a lot about this problem, but I just wanted to give you some background here. The total pressure is just going to be equal to our two partial pressures added together. So let's see, P total is equal to 1.4 atmospheres plus 0.2 atmospheres. I mean, this is probably pretty obvious, right? 1.6 atmospheres is what I'm getting when I do that math in my head. Okay, another way that this problem can be asked in a somewhat harder way is they give you all these pressures. Okay, we have pressure of nitrogen, 1 atmospheres, pressure of oxygen, 345 millimeters of mercury of pressure, and then 145 kilopascals of, I don't know, let's call it gas C. I'm assuming this problem is missing some sort of gas there. Now we're being asked for the total pressure of the gas. Okay, what's somewhat harder about this problem is all the gases are given to us with different units. You can't just add them together. You can't add 1 egg plus 1 dozen eggs and then get 2 dozen eggs. You have to make sure that you have the same units first before you add it together. So let's see. Personally, I'm partial to converting everything to atmospheres. I feel like atmospheres is the easiest unit to think about because it's just the pressure at sea level of Earth. So let's convert everything to atmospheres here using our conversion factors from before. Let's see. Nitrogen, we already know that's 1 atmosphere, so nothing needs to be done there. Oxygen, it looks like we're starting with 345 millimeters of mercury. So to convert that to atmospheres, let's use our conversion factor. We know that there are 760 millimeters of mercury at sea level, which is what the pressure is in 1 atmosphere as well. So millimeters of mercury cancel out. We have to do 345 divided by 760. So let's do that. And I am getting about 0.454 atmospheres of oxygen for that partial pressure. The next conversion we have to look at here is the kilopascals. So we are given this third amount of pressure here, 145 kilopascals. So let's convert that here. I believe the conversion factor was there's 101.3 kilopascals in 1 atmosphere. So in this case, kilopascals cancel out, and now we do 145 divided by 101.3. And I am getting about 1.43 kilopascals as my answer here for that gas C, whatever that is. So what is the total pressure of this gas? Just like before, you add all the partial pressures together to get that. So we're going to do 1 plus 0.454 plus 1.43, and you should get around 2.884 atmospheres for your total pressure. If you're rounding to the correct number of sig figs, in this case, you're going to round to the ones place, so that would just be 3 atmospheres if you want the most technically correct answer. Okay, final example here. In real life, often what they do is they give you these tables of data that you have to use. Often, if you're doing an experiment, you have to actually Google, like, I want to collect gas over water, so I have to think about water vapor pressure. When you Google water vapor pressure, they'll give you a table just like this, and you have to go and find what the water vapor pressure will be. So it turns out water vapor pressure is pretty much always the same. It only changes based on the temperature of the water. So it looks like maybe the room temperature or the water temperature, they're at 27.0 degrees Celsius. So a sample of oxygen is collected over water at 27.0 degrees Celsius, and the total pressure of this gas is 1.2 atmospheres. So given this table of water vapor pressure, what is the pressure of the dry oxygen gas from this sample? Okay, dry oxygen gas. Sometimes we call gas dry, or we'll say like dry gas, dry oxygen gas, dry atmosphere. And whenever you hear that referred to as gas, that just means the pressure of gas or the composition of gas without water vapor included, because we think of like water as wet. So if you take the water out of the gas, then we call it dry gas. Over here in this table, what we're going to look for is just 27. So already here, this is the partial pressure of water vapor at 27 degrees Celsius. Now it gives us the partial pressure in millimeters of mercury and in kilopascals, but it looks like we do not get it in atmospheres, which is what we want to work with right now. So we got to make a conversion. I'm going to use these millimeters of mercury here. So I'm going to do 26.7 millimeters of mercury, and we're going to say of water vapor, H2O, and let's convert that to atmospheres. There's 760 millimeters of mercury in 1 atmosphere here. So we're going to do that 26.7, and we are going to divide it by 760 to get 0.0351 atmospheres of water. So you notice that when you collect gas over water, not a lot of that total pressure of the gas is actually being contributed to by the water, but it's still noticeable. There's still something there. So let's go ahead and calculate this. If the total pressure is equal to all the individual gases, looks like there's only 2 gases here, oxygen and water, then let's just use that total pressure, 1.2 atmospheres, to figure out the pressure of the oxygen if the partial pressure of the water vapor is like 0.0351 atmospheres. So it looks like we just have to subtract that from both sides. And it looks like the pressure of the oxygen, once you subtract that, is going to be 1.1649 atmospheres or so. Now, if you round to the correct number of sig figs, this answer is kind of funny. It's going to be 1.2 atmospheres again. But either way, that is going to be the partial pressure of oxygen, according to our calculations. All right, the final part of this lesson, we are just going to talk about a couple more things here. These are more conceptual rather than skills-based, but it's basically to describe what is going on with gases, and then just give background for our future lessons in the coming weeks. So first of all, there's this term called kinetic molecular theory, and basically it is a set of assumptions that make our lives easier. So we were going to make some calculations using gases, and we are just going to make some guesses as to how they behave. Now, these assumptions about how gases behave, how they go about and bounce off walls and stuff, they allow us to make calculations that are like 90% easier and pretty much as accurate as more advanced chemical engineering math. And these assumptions are called kinetic molecular theory. It's just a series of what we call postulates. And these postulates are just like facts that are our assumptions. So first of all, and by the way, none of these are true, but they're mostly true. Like if you assume that they were true, then you'd probably be mostly correct. So the first postulate here says that the volume of individual gas particles or molecules can be assumed to be 0 or negligible. So all these, when you walk around a room and you see all these gas molecules around you, well, it's hard to see. It take up almost 0 space. So we're going to assume that gas particles actually do take up 0 space. They have 0 volume. Second postulate, gas particles are in constant motion. All of the collision of these particles with the walls of some certain containers are the cause of the pressure exerted by the gas. This one's just straight up true. All all the air pressure that we feel is pretty much just due to those gas particle collisions against you. Third postulate: gas particles do not exert forces upon each other unless they collide. And if they collide, the collisions are perfectly elastic. So when you get to advanced chemistry, it turns out molecules do exert forces upon each other if they get close. We're going to assume that does not happen to gas particles because they are like so spread out. Now, in the very rare event that a gas particle manages to hit another gas particle, I don't know how, they have zero volume, we are going to say that collision is perfectly elastic. Or when a gas molecule has any sort of collision, it's going to be perfectly elastic. So what does it mean when something is perfectly elastic? That means that all kinetic energy is conserved. More of a physics term here, but I want you to think of like a bouncy ball. So when you like bounce a super bouncy ball, it pretty much goes to the exact same height that you bounced it from. That's a very elastic collision. Now, let's say there's a car crash, and trigger warning for everyone who has some sort of traumatic experience with car crashes. I know I have. When a car crashes, it's designed to crumple, absorb all of that energy, and then it does not conserve kinetic energy. Everything just kind of stops. So elastic collisions are really bouncy. All the kinetic energy, all the movement is conserved. And then inelastic collisions, things that aren't elastic, that energy goes away and movement kind of stops or slows down a bit. Okay, fourth postulate: the average kinetic energy of all these gas particles, that is assumed to be directly proportional to the Kelvin temperature of a gas. So average kinetic energy is Kelvin temperature of a gas. Kelvin's just another unit of temperature, like Fahrenheit or Celsius. Now we're going to think about what Kelvin is. Also, this should be proportional. So if your gas follows all of these postulates, it is said to be an ideal gas. Just an imaginary gas that follows perfect theory. Now, there is no such thing as a gas that is an ideal gas, but most gases are mostly ideal gases. Like they're 95% of the way there. Just like, most people are good people, right? But enough of that. Let's talk about what this Kelvin thing is. Kelvin is another unit of temperature, and all calculations with gases, all the stuff we're going to do in future units or lessons or whatever, they're going to be done in units of Kelvin for temperature. If you're given Fahrenheit, convert it to Kelvin. If you're given Celsius, convert it to Kelvin. Now, 1 Kelvin is like the same size as 1 degree Celsius. Like they're the same kind of unit size, but they have different starting points. 0 degrees Celsius is the freezing point of water. But Kelvin, when Kelvin starts at 0, we call that absolute zero. Absolute zero is the temperature which there's no heat energy. No heat energy, that basically means no particles are moving at all. You can learn about that more advanced chemistry, but basically 0 Kelvin is way, way colder than 0 degrees Celsius. In fact, 0 Kelvin is 273.15 degrees Celsius colder than 0 degrees Celsius. So how do you convert between the two? It's just simple addition or subtraction. If you want to get degrees Celsius, you take the Kelvin that you have and add 273 to it. If you want to get to Kelvin from degrees Celsius, you take the amount of degrees Celsius that you have and you subtract 273. That's it. Now you just got to make sure that you're always in units of Kelvin before performing any calculations of gases. And we'll see examples of that in the coming weeks. By the way, I did find this interesting little graphic for y'all. It looks like the size of 100 degrees Celsius and the size of 100 kelvins are the exact same in these thermometers. It's just that, at boiling temperature of water and at freezing temperature of water, we have different starting points here for those scales. And just for fun, we do have the F word in chemistry. Please do not use it. Fahrenheit here. We notice that, of course, the freezing point is 32 degrees Fahrenheit. And actually, interestingly enough, when are Fahrenheit and Celsius equal? It's when they both reach negative 40. So that's one way you can think about how converting between the two. That's all I have for you all. Please make sure that you follow your teacher's instructions on how you're being graded, on what assignments you have to do. And after you're done with these notes, make sure you know how to do everything in these notes, describe all these things, and finish that practice.